So uh, there's some situations here where you need to use what's called vector subtraction, but to me it's better to just think of it as correcting course, okay? So I'll give you a couple of examples, but before we do, I just want you to recall that our little mantra for adding vectors together is add vectors tip to tail, okay? Okay, and they're sort of like adding is vector 1 plus vector 2 plus vector dot 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 is really just, v1 plus v2 plus v3. Okay, that's kind of what we've talked about before. And if we put it graphically, that could be go this way, followed by, that way, followed by, I don't know, whatever. Okay, and then the sum of all those vectors, ends up being from where you started to where you finished. Okay, so we call this the net vector if you want. Okay, so all the vectors added together give you the net vector. All right, sweet. So a quick example of something that we've done with this would be, you walk north. Let's fix that up. You walk north some, say 10 meters. Then you walk east some value, and then we even learned, we might walk off at some angle, and we've figured out a method for solving something like that. And the resultant vector would be the sum of all those input vectors, right? So far, so good. No problem there. If you're set up with a problem like that, you'll be just fine. But there's another use for vectors, and this comes in when we talk about relative motion or relative velocities. Okay, I'm going to teach these right out of the gate, and I think it flows nicely from what we've been talking about already. So relative velocities. And we'll start with kind of a simple riverboat problem. So let's imagine that you have a little river here, okay? And that river has a flow to it. So let's say it's flowing north. Let's fix that. I don't know, and we'll make it flow north at like 5 meters per second. Okay, and we'll put a little boat in here. Okay, and we'll say that that boat is attempting to go across the river. Now, you got to think about this a little bit. If you're the person in the boat, you just start to row. Okay, you do no correcting at all. Use your little oars out in the water. As you row from your perspective straight across the river, you're actually on a surface that's moving in this direction. So what'll end up happening is your actual motion is going to end up being the sum of your two input vectors here. Whatever velocity you're rowing at, v1, plus the velocity of the river, v2, add together to give you velocity 3, which in this case is over in this direction somewhere. Okay, so what you have to do if you desire to go straight across is you have to kind of like row into the current, right? So that your velocity vector plus the river's velocity vector end up giving you the desired vector. So we call this like correcting course. And in order to do that, we do vector subtraction. So in the kind of language we've been using then, this ends up being your net velocity, right? Okay, so in order to correct it, and we'll do a little bit of, we'll throw some numbers in here in just a second. Make this a little bit longer, okay? So we would say, if no correction, boat travels along v net. That's its velocity, the direction of its velocity, okay? But if you try to correct this, you have to think about this in a slightly different way, okay? So the way I think about it is, well, what we want is we want our v net, we want our net velocity to actually end up being this, right? And in order to get that, we have to account for this vector. So we have to paddle in a direction such that we end up arriving, I guess if you want, at our v net. So you kind of have to approach the problem kind of in a backwards way, right? So you have to turn this into your v1 and this into your v2. Okay, so you have to paddle off down in this direction. The river pushes you back this way, and you end up traveling straight across. Okay, so this corrected velocity ends up giving v net. Okay, so with a scenario like this, with a river flowing, there's basically like 3 types of problems you can get, maybe 4 types. So we'll just look at what could possibly happen here. Let's make this 1 kilometer wide, and let's just quickly review our. Yeah, that's pretty wide. Whatever. It's the Mississippi. It's a giant river. Okay, so all right, so let's do problem 1. Okay, so you might get asked a problem, say something like, if the boatman does not correct calculate A, V net, B, time to cross. And you're missing one crucial piece of information, obviously, and that is how fast the boatman can row. So he rows at 8 meters per second. So that's dealing with the first problem here. That's dealing with this up here. All right. So this is kind of a standard vector problem. Instead of dealing with displacement, though, we're dealing with velocity. And the same logic applies to any group of vectors that you come up with, right? It could be force vectors. It could be gravitational field vectors. It could be magnetic field vectors, whatever. You sum them in this way, okay? So all we're going to do is we're going to say, okay, so V net then, of course, is going to be V1 plus V2. In this case, that's 8 meters per second to the east, right? Plus 5 meters per second to the north. And we'll just do a standard vector addition with that. Why does it go to that one right away? So 8 plus 5 plus we want this. Okay, fire in our values. So we got to do a little Pythagorean here. Okay, and we're going to want theta. So that's going to be the inverse tan of opposite over adjacent. Okay, solving your Pyth is you are going to end up with a velocity of 9.4 meters per second at 32 degrees north of east. Now, it's a good practice to just step back at this point and think about what that really means. Okay, so you know, if this is 8 meters per second here, right, and this is 5 meters per second, this angle ends up being 32 degrees, and we get 9.4 meters per second. Now, this is not what the person in the boat necessarily is going to observe. Okay, if you think about it, let's say this person's out in the middle of this gigantic river, and for whatever reason, he can't see the shore, or she can't see the shore. From that person's perspective, they're just rowing on some water, right? If they can't see the shore, they'd have no perspective that they're actually doing anything but just rowing right across this thing. So this is as observed by a stationary observer. So that'd be like, say, somebody standing on the shore with some binoculars or whatever, looking out, right? They're seeing this boat going off in this direction. Or if you want, like a helicopter hovering up above this scene, and that's sort of the view we have, right? We're stationary. So you have to keep that in mind, right? Motion is relative, and the perspective of the observer is different than the perspective of the person actually undergoing the motion, okay? So you got to watch and think about what exactly we're talking about here. Now, in the second scenario, which we'll get to in just a second because I realize we need to calculate time to cross. So for time to cross, it's sort of interesting. Some people are going to be tempted to throw in 9.4 meters per second, and they're going to say, okay, well, I have 1 kilometer divided by 9.4. That will give me my time to cross. What's wrong with that thinking? Why can't we just go 1 kilometer divided by 9.4, boom, that will give me my time to cross? And if you're a little confused as to what we're talking about, we're just saying the time is equal to the total displacement covered divided by velocity. So it's just the alternate form of v equals delta d over delta t. So why can't I just do that? Think about it for a second. So if I want to know the time to go across here, right? I think about this in sort of two different ways. The first way is to understand that directly across this river is 1 kilometer wide. Okay, so it's 1 kilometer. And and you can think of this straight across line, like if I laid, say, like a big log across the river, that log would flow along and it would keep perpendicular to the shore the whole time. Okay? Along that line, I'm traveling at 8 meters per second. Okay? That's one way to look at it. The other way to look at it is to say, well, from the observer's point of view, I'm starting here and I'm ending up over here. And from his point of view, okay, that is going to make that 32-degree angle we're talking about. Okay? So the displacement is along this angle. So I can either figure out this long displacement here and realize I'm traveling at 9.4 meters per second along this long displacement here and do it that way. Or, I feel like these two should line up right there. Okay. Or I can just take the 1 kilometer wide and realize that along that vector, I'm traveling at 8 meters per second. Why don't we do it both ways just to prove that it's going to be the same value in the end? Okay, let's do it both ways. Okay, so time way one. And this is where being a bit of a physicist sort of comes in handy. Thinking about the problem before you just sort of blast into it is a really important skill to learn, okay? People will often just tackle this, they'll throw that 9.4 in the 1 kilometer and move on without thinking. That's a space monkeying approach. You be careful not to let yourself do that. So we have 1,000 meters directly across the river, and along that directly across path, you're traveling at 8 meters per second. Here's one more way, just before we actually do it, to think about it. Think about this guy rowing in the boat, right? If he's in like say we put a box over him or something, we put a shield so he can't see the shore, right? He's just rowing in a straight line, right? He's just rowing along in a straight line. It makes no difference to him whether the river's moving or not, right? The river could be dead still or the whole river is moving. From his perspective, he's just rowing straight across. So if we do it from his perspective, that's the straight across thing. If we do it from his perspective, that's the angled thing, okay? Same motion, two different views of it, all right? I'm going to talk about Galileo in a second, but we'll solve this two ways and see what we get, okay? And then there's way two, which is a little bit more tricky. So the velocity in way two is 9.4 meters per second, but he's not going 1,000 meters, he's going a longer distance now, right? He's going along this value right here. So if we think about what he's actually traveling here, I'll just quickly draw it so we remember. You've got this. You got 1,000 here. You've got some value here which we have not dealt with yet, but we might. Hang on, we'll see. We've got 32 degrees there. We've got this value being something we don't know, and we know this is 1,000 meters wide. Okay, and we also know that cos of 32 degrees is going to be equal to adjacent over hypotenuse. So 1,000 meters divided by question mark. So question mark, the hypotenuse that we have then should be equal to 1,000 over cos 32 degrees. So we can put that in here like this, 1,000 divided by cos 32 degrees divided by 9.4. Let's rewrite that so it looks a little nicer. Okay, and we should get the same time that we got up there. So there we go, 125 seconds either way you do it, all right? Either 9.4 along the hypotenuse or 8 across the direct, all right? So you can get the same value in both cases because it's the same motion, all right? Now the last thing you might be asked, which I didn't in the question, but the last thing you might be asked is how far downstream did this person end up? How far downstream did they end up? Okay, so we'll just tack that on here. How far downstream? Question mark. So really what you now have to do is figure out, well, what is their velocity along this? And we already know what it is. It's given to you. It's 5 meters per second, right? It's the flow speed of the river times just the time that they do it for, right? 5 meters per second times 125 seconds. That's how much time you're traveling. So 5 times 125, 625. And there we go. So that is to the north. North of directly across. Okay, let's look at the second here where we're going to actually correct for the flow of the river. Okay, so this is part 2. So we can get a bunch of questions asked here. Now, this problem can be approached in a couple of ways. The first way is probably the simplest way. And you will be asked something like, the boatman needs to have, okay, there we go. It's like my brain wasn't working for a minute. The boatman needs a net velocity of, say, 9 meters per second east. What velocity must he row at relative to the shore? So just jump in here and I'll say, to subtract vectors, comma, add the opposite. We're now given V net, right? It has to be 9 meters per second. V2, we know what it is, right? It's 5 meters per second north. And we have to figure out what V1 we need to have such that V1 plus V2 gives us the V net that we're asking for. So here's our little equation, and let's just rewrite it. So now what we'll have is we'll say, well, V1, which we need, is equal to V net subtract V2. Okay, V net subtract V2. And to subtract vectors, we add the opposite. That's our second vector mantra after vectors are added tip to tail. Okay, this is mantra 2. So to add the opposite, we're going to do this. We're going to say, okay, so we're going to say we need V net, so we need 9 meters per second east plus the opposite of V2 which was 5 meters per second to the north. So we add 5 meters per second to the south. Brilliant. So look at what we just did. We took this, our V-net, and we added to it the opposite of this. So let's just flip this over. Oh no, I can't do that anymore. Draw a new one in. We flip this guy over, and look what will happen. V-net plus the flipped V2 will sum up to give us V1. Okay? Now, that's the like mathy way of doing it. Just think about it. If it's flowing to the north, I got to aim my boat somewhere off to the south, right? That's all you have to do. So, yeah, here we go. We just solve for V1 now. Uh-oh. Okay. So, yeah, it's going to have to be a new vector triangle. So we want that. We want to add this to it. Okay. And you want to go off at this angle somewhere down here. Okay, so let's solve for that. So Pythagorean. Okay. And we want to solve for theta. We need to know the angle. So that's going to be the inverse tan of the opposite over the adjacent. And we'll just pause and solve. Okay, so solving for the hypotenuse of our little triangle here, you get that it needs to travel at 10.3 meters per second, 29 degrees to the south of east. And what will end up happening is that the boat will get pushed back on course by the flow of the river, which remember is actually upward, and he will travel along the river at 9 meters per second. So now we might get asked the time, okay? So there's A, B. Well, what about time now? Time to cross. Well, that should be easy. You should get what that should be, right? Time to cross is going to be however wide I'm going divided by however fast I'm going. So in this case, 1,000 meters divided by 9 meters per second. So 111 seconds, assuming these are all sig figs, and this is 9.00. Okay. But yeah, rounded to approximately 100 seconds if we want to follow sig fig rules. Okay, let's do one more variation on here. Okay, variations on a theme. Was there a C? I don't think there was a C for this one. So I'm just going to grab this picture again. Bring it on down. So this is a slight variation. So what if, instead of knowing how fast we want him to go, we know how fast he can paddle? That's a slightly different problem, isn't it? So here's a variation, and you might see one like this. The boatman, it's not how you spell boatman, the boatman can row at, how fast can he row at? He'll keep it at 8 meters per second max. So that's different than this last question because we just figured out that he has to row at 10.3 meters per second. What angle must he travel at to have a heading, to have an easterly heading? Okay, so why is this different? Well, the reason this is different is because now we know that this is 8 meters per second, and we know that this is 5 meters per second. What we don't know, though, is what is that and what is this angle? Okay, so it's still a vector problem, but you can't solve it necessarily in the exact same way that you were solving before. So how are we going to end up dealing with this? You're going to use trig to get the angle, and you're going to use pith to get the straight across. right? But you're going to end up with different angles and different values than you had in the other types of questions. So what do you want to do first? Let's get the net here first. So remember that c squared equals, oh geez, let's do it right. C squared equals a squared plus b squared. So in this case, the hypotenuse is c squared, right? And we want to get b squared. And we have a squared, right? So what we have to do here is we have to say b then is equal to the root of c squared minus a squared. So you have to do some algebra with your pith, okay? So 8 squared minus 5 squared equals, so you're going to get that is actual velocity of travel is 6.2 meters per second along the VNet route, along this value here, okay? And then angle, well, you have the opposite and you have the hypotenuse, okay? So theta then should be the inverse sine of the opposite over the hypotenuse. So you get 38.7, we'll say, degrees south of east, okay? So if his max velocity is 8 meters per second, he's going to have to take a larger angle, right? He's not traveling as fast as he was in the earlier question. So depending how fast he can row, his angle will change, right? Because what that does is if he can row faster, this value is larger. He's traveling for less time, and therefore less deviation is necessary, okay? And there is going to be a position where he's just not able to row fast enough to go straight across, right? You can always get across, but you might not be able to get straight across if you can't row fast enough, okay? So then the last thing you might get asked is, okay, so how much time to get across? Okay, so in this case, this is his velocity in the straight across direction, okay? So that is what he's covering the 1,000 meters over, all right? So keeping all this stuff straight can be a bit of a challenge. And that's on you, the physicist, to make sure you're keeping track of everything and you know what you're talking about with all these different numbers. So you get just over 161 seconds now to get across there.